want the additional mechanism, it's totally fine to not have NACs. Just don't bother doing it. And TCP, in fact, doesn't have negative acknowledgements. So with that, we now know how to deal with packets that can be lost or corrupted. What about packets that get delayed? So let's say this packet here gets delayed, makes it on its way to this receiver, checksum worked out, you got back an ACK. Is there any problem? Not necessarily, right? If your packet was delayed but got there before your timeout, you're just fine. If it got there after your timeout, what would you do? The sender will send a duplicate. The receiver will send a duplicate, another ACK. So we now got both two packets. The packet was delivered twice at the receiver and the ACK was delivered twice at the sender. But it's not the end of the world. This is still a correct delivery of the packet. Okay? So we're good. We don't need any new mechanisms to deal with delayed packets. If you walk through the same but reason about delayed ACKs, you'll see that we're still fine. So we can also deal with delayed packets. What about if packets are duplicated? So what does a duplicated packet mean here? It means that the network somehow generated a duplicate packet and sent it. It sent a copy of the packet to the destination. Your first thought, really the only thing that's interesting about this case is why would this even happen? This is very, very rare, but it has been seen to happen on the internet. And it's usually because you have some kind of link technology that is doing reliability at that link. And so at that link, one end, the sending side of that link, decided to retransmit a packet because it thought the other end didn't get it. So it retransmitted the packet. And then the receiving end of that link forgot, or it had deleted the state that told it that it had already forwarded that packet, and so it sends it twice. So it's really this corner case, very, very few occurrences of anyone ever seeing it, but actually Vern Paxson, who was on the faculty here, was the first to actually publish that this was a thing that happened. And he went to the router vendors and said, your router is, your link technology is duplicating packets, and they were like, no way, it doesn't happen. And then he was like, I can show you that it happened, and after much back and forth, he actually convinced them that they had a bug in their implementation and this could happen. So rare, but happens. From our point of view, let's not worry about how it happens. If it happens, what do we do in terms of reliability? Is this something we have to worry about? No, exactly. You got a duplicate, you sent another ACK, the sender got two ACKs. The sender was already prepared to deal with that. Okay? So we're good. So with that, we actually know how to deal with all the things that can happen when you have a single packet case. We don't have to worry about reordering just yet because we're only talking about a single packet case. Okay. So we now know how to reliably transfer one packet across the internet. It's a very simple algorithm. Sender sends a packet, sets a timer. If it doesn't receive an ACK in time, it resends the packet, resets the timer. Receiver, very simple. You get a packet, you send an ACK. Okay. Any questions on this? This should be really simple. Okay, so what have we learned? What we have learned actually are the building blocks for a solution. We now know about checksums, feedback, either positive or negative ACKs, retransmissions at the sender, and setting timers that when they fire, we're going to retransmit. We also have in place semantics of a solution, right? That both the sender and the receiver could see more than once delivery. So there are no questions. I'm going to move on to sending multiple packets. So now we're going to talk about sending multiple packets. The only design component we actually have to add to the ones we had is the notion of sequence numbers. Okay. So now we're going to say that data packets carry a sequence number, and the ACK tells you what sequence number it's ACKing. Okay. So like here you have packet 1, and then you have ACK 1, then you send 2, and you're ACKing 2. That's really the only mechanism we absolutely require. So with that, we have all the necessary building blocks to actually build a reliable protocol on the internet. The straw man that all the textbooks will discuss, and somewhat surprisingly, some people actually use this in practice, wouldn't advise it necessarily, definitely not on the internet, is what we call a stop and wait protocol. Okay, and the stop and wait protocol is as simple as can be. It uses the single packet solution we just delivered. It says you wait for packet I to be acknowledged before you send the next packet I plus 1. This is actually a correct, reliable delivery protocol. It's also an extremely inefficient one. You're sending one packet every round trip time, in the best case. Okay. So if you look at it visually, this is what we're doing. Okay. Send packet 1, wait for the ACK. When I was waiting for ACK 3 and I didn't receive it, I took a timeout, resent it, and only after I got ACK 3, I sent packet 4. This is actually a reasonable protocol if your round trip times are really, really tiny. So sometimes inside a machine, you will see different components on a server doing something like stop and wait. But across the internet, where you have hundreds of milliseconds round trip times, this is not something we want to do. So what would you do to make this go fast? Standard trick in computer science. Yep. Yeah, so parallelism, right, or pipelining. Just send multiple packets out at the same time. We call this having multiple packets in flight. What does that mean? That the sender sent out multiple, it's okay to transmit lots of packets that have not yet been acknowledged. So you can have multiple packets in flight that are waiting to be acknowledged. Okay. And so now things start to get a little bit more interesting. So this is what we call window-based algorithms. The basic idea is we're going to tell the sender you can send up to W, some parameter W, number of packets in flight at any time. W is what we call the size of the window. Okay. And so a simple algorithm, just extending what we did so far, was to say the sender can now send W packets, and when it gets one ACK back, it's going to send the next packet in line. Okay, so what does that look like? Let's say here we had a window of 4. So the sender got to send packets 1 to 4, and now it's waiting. Okay. So its window at this point is 1, 2, 3, and 4. These are the packets in flight. Again, packets that have been sent but not acknowledged. When the sender gets back ACK 1, it's now okay to send 5. So now its window is 2 to 5. So we call this sliding the window forward. When you get the ACK for 2, you slide the window one more time, and you're allowed to send 6. Okay? So at this point in time, your window is packet numbers 3 to 6. These are packets, W packets that you were allowed to send. You're waiting for ACKs. Everyone good with this? Yeah. Okay, so going back to, we said we had all the necessary building blocks. In practice, we have this one more parameter or mechanism, that's the window and the window size. We do this for efficiency, not for correctness. The stop and wait protocol we had was correct. It would correctly deliver packets. This is all about performance and optimizing for efficiency at this point. But once you have windows, there are a lot of design questions that open up. First is just, what is that window size? Right? How many in-flight packets do you want? The second is the nature of the feedback, because if you think about it now, the receiver is sending all of these ACKs one after the other back to the sender. Could it be sending more useful information than simply, I received packet 3? It could be sending you something about the history of the packets it's received. You could then use that to detect loss, right? As we're going to see, depending on which ACKs you get, it's a pretty good indicator of which packets the receiver did not receive. So maybe we can do better than waiting for timeouts. And finally, how do you respond to loss as you start seeing these ACKs come in? So this is going to set up the kind of the questions that form what we call a window-based reliable protocol. Let's start with the first question. How big should the window be? Thoughts? How big a window do you want? What are the considerations we have to worry about? Yep. The bandwidth of the link, right? So you want to take advantage of network capacity, this notion of filling the pipe, send as many packets as you can. At the same time, what should you worry about maybe? Yep. The MTU of your network. Yes, I wouldn't have said so much for reliability because, say more, because if you send something more than the MTU, the network will fragment it and send it out, which the fragments will still arrive at the destination. So remember that now we are up at the TCP layer, at the transport layer. So all the reassembling of fragments and all of that has been done by your layer 3 implementation at either at the receiver. So you're, at your transport layer, you're now receiving the full packet. So we actually don't have to worry about fragmentation at this layer. Yep.
Question. So how would a router prioritize like trying to send out 2 files at a write at the same time? Does it send out the first file first, like break it down and fragment it, or like would it do both?
So remember, the router is just getting packets, right? And so if your question is between 2 packets, one of them needs to be fragmented, the other not, is that?
Like 2 files, I guess, yeah, like 2 file layers, 2 separate files.
So your router is not seeing files, it's just seeing packets, and it's just taking one packet at a time and sending it out. And we could be doing more fancy scheduling, but for most of this, certainly for this discussion, we're saying that routers are just doing FIFO order scheduling. So whatever order the packets come in, I'm going to send them out. Yep.
Question about setting window. If you receive an act from 2 but not from 1, what do you do?
We're going to get to that. Hold on to that question. Okay, so other things you should worry about in terms of picking your window. You want to make full use of the pipe you have, but you also don't want to overload links. Right? Because if you overload links, you're going to end up with dropped packets. Not a good idea. So this is a problem we call congestion control. And the other concern, which we haven't yet touched on, but we're going to start to worry about, is you also don't want to overload the receiver. Right? Because the receiver can only pick up packets at some rate, has a certain amount of buffer space, so you don't want to overload the receiver. We call this flow control. For this lecture, and until we get to congestion control, ignore the second 2 concerns. They are concerns. We'll deal with them when we get to congestion control. So for this lecture, just say that we're focusing on the first goal, which is we want to fill the pipe, right? And if we want to fill the pipe and fully use network capacity, what does that mean in terms of the sender behavior that we're looking for? What it means is we want the sender to always be sending for the entire round trip time. We want the sender to be busy transmitting. Okay? So for an entire round trip time, I want the sender to be busy. What that means is that when an ACK comes in, the sender should pick up the ACK and send out another packet. Let's look at that visually. I think it's much more intuitive when you look at it in terms of an example. So we said in this case your window was 4. And the sender had sent 4 packets, got these 4 ACKs. Your round trip time in this case is the time it took you for the packet to get to the receiver and the ACK to come back. If you notice, there was a large fraction of that time that the sender was just sitting there, doing nothing, right, waiting for that ACK to come back. Because your window was too small in this case. 4 packets was not enough to keep the sender busy. What we would have liked, ideally, is that the sender is always busy sending out a packet, and it had a larger window that allowed it to keep sending for the duration of the round trip time. Okay, so what does this mean? When we think about it more rigorously, what we're saying is, let's say that B is the minimum bandwidth of a link along the path. It's what we call the bottleneck bandwidth. Okay. So there's no case in which the sender can be sending faster than the bottleneck bandwidth. Right? That's as fast as it could send. But you also, under the assumptions we've made, we don't want the sender to be any slower than that bottleneck rate, because otherwise you're wasting capacity. And so what that means is that for this setup, we want the sender to be sending at the rate B, this is the bottleneck rate, for the entire duration of the round trip time. Okay. So this gives us our condition that we want window size, the W parameter, to be set such that the window size, which is how many packets you can send, times the packet size, let's assume a constant packet size here, is the round trip times delay times the bottleneck bandwidth. Is this making sense? Let's look at it visually, because we all trip on this. So in this case, what I'm showing you here is one link, but I'm showing it to you in a bidirectional. I've split up the path going from the sender to the receiver and coming back from the receiver to the sender. Because remember, a link is bidirectional. Right? I can send B bits per second and I can receive B bits per second at the same time. So in this case, I'm saying my window at the sender should be 6 packets. Right? And if you look at the pipe, I have 3 packets on their way to the receiver, and I have 3 ACKs coming back to the sender. So there's 6 packets that the sender has sent, but they're not acknowledged yet. So the thing that confuses people is they look at the pipe and they say, it can only hold 3 packets. Why isn't my window size 3? Right? But if you think about it, if we'd said the window size was 3,